Hold that. Let's come back to that if you don't mind. Yes, let's do about 2 minutes. There's something that TI does, I don't know why, when you do these distributions that looks like that. And I don't have a good answer for you, but I have a workaround for it, so. Right?
Are you teaching 244 at the same time next term?
No, I got the 8:15 one.
In the morning?
Yeah, yes.
So I'm just gonna say, I'm gonna take you next turn,
Okay.
It's Monday.
if you allow me.
Yeah, it's a Monday, Wednesday.
Yeah.
What they said, I'm gonna trust them.
8:15.
Yeah, I think my 243 is on
Yeah,
243.
8:15 is like
As long as it's not like,
It might actually be
20th,
internet.
I'm scheduled for
Monday,
20th.
Wednesday.
Yeah.
Okay, you got some probabilities? And I heard over here there was a pattern that we were starting to see. Yes, there's definitely a pattern. So, how many? What's the chance of a 5?
4.
Yep. Chance of a 6? Chance of 7? Chance of an 8? Careful! Does it keep going up? Yes. Goes back down again, doesn't it? If you start counting how many ways you can get 8, it actually starts decreasing. Yes. And then 4. And then 3. And then 2. And then 1. Yeah, all the way down. Yes, yes, yes. Yes. Interesting. Yes, interesting. So, the idea, and what does that add up to? You can check it. It's kind of cool, actually. Yep. Sums up to 1. So there's your distribution. Now, what Hattie just asked, actually Patrick asked a very good question. I'm going to get his question first, then yours, Hattie. Patrick asked, how do you enter those into your TI? And there's 2 answers to that question. One is you just simply start plugging 1 divided by 36, 2 divided by 36. Let's look at it with 1 divided by 6. The other way is you can be a little bit tricky. And I don't like trickiness. I like cohesiveness, but not trickiness. Probability distributions, I focused, and I will continue to focus on the T-table representation of them, where you've got an X column and a P of X column. There are other ways to look at them. Graphically is one way. So you can do a T-table. You can also graphically, which we'll show you in a second, we can get the graphical representation of these things on the board, which is fantastic. And you can also do equational values of them. For example, Jen's like, stop talking about that right now. But I want to answer Patrick's question as best as I can. This whole distribution for a single die can be wrapped up in kind of Math 111 very easily by saying x equals 1, 2, ... 6. P of x equals 1/6. Now, Jen, I'm with you in that that's a little foreign because so much is hidden in what's actually going on in the distribution. But this is a way, and this is a way most Introstat textbooks used to teach this stuff, was by give the domain, give the range. Kind of like you did in 111. Domain, range, domain, range. This one's a little bit of a, this one's goofy, believe it or not, but you can actually write this one as an equation too. In this one, x can be written as 2 through 3, all the way up to 12. Watch this. I figured this out in class with the other class yesterday, and it was an unrelated question. You can actually plug these numbers into an equation to get this out. And here's the equation. If you plug those x values into that equation, you'll get those probabilities. We sat down, we actually did some 111 in class yesterday. It's kind of insane. Because they said, is there a shortcut? And there is a shortcut. You can plug this into L2, and when you press enter, all of these will pop into L2. But I'm going to go with Jen. Most students start seeing this and they start feeling like, exactly, sick to your stomach. But these are called PDFs, probability, distribution, or density functions. Don't worry about it too much. I like the T-tables. The reason I don't like these very much is because if I asked you based on this, what's the most likely sum?
7.
Okay, but you're not basing that on this.
Yeah.
You're basing that on this. That's why I like these. These actually show you everything that's going on without doing any mathematics. That's why I like the T-tables. But Patrick, if you want, you can generate equations with these things and generate equations, but I think, personally, I think it's much nicer to just look at the results of the table. Is that fair? That's one question that came up. Hattie's got a question too. She entered the distribution, wanted to take a look at it. Thank you for that. That is awesome. You should always look at your data and see what it looks like. Because Kate had a theory about this. She's like, it's bell-shaped. Kelly, go ahead. Oh, just stretching. I'm keeping it open in stretches. I apologize. Let's take a real quick look at this. Here's the book. Okay, there's my distribution right there. Okay, L1, L2. It changes them to decimals to you too, as you guys figured out. Now, if you try to graph this, let me set up a graph. So I'm sure they're turned off right now. let's turn a histogram on. Histogram, L1, L2, just like we usually do, yeah? And you press zoom, 9 like you usually do. Stupid. Dumb. I don't know why this happens. I wish I had a better answer for that. I don't know why this happens. But this is why, as Megan will attest, I always finagle with the windows. Because you can fix this. You can fix this pretty easily by going into the window and messing around. I don't know why it does it, but we can ignore it and just go to window. And then I look, I can see right away what the problem is. It's that. That's the problem. Your scale is set at 10. Why? Beats the hell out of me. It decided to do that. I don't know what code it uses to pick that window. But you set it to 1. You set it to 1. And while you're in, now why 1? Why am I picking 1?
Because we're going back how many pips are.
Right, if you look at your pip numbers, it goes from 2 to 12 by 1s. So it makes sense to view it by 1s. See how it starts at 2 up there? 22 is too big. I'm going to make that 13. Why 13? Why not 12? Remember the reason for this? I brought it up a few times in class. You got to go one past your last one to have the bar be a bar and not just be a line. So the first, I'll show you in a second. I'll show you in a second what I'm talking about. I'll show you in a second what I'm talking about. Everything else is probably bomber. As a matter of fact, this is too high. This Y max is too high. The highest probability we have is 1 in 6, yeah? And that is what as a decimal? 16.6666%. So I'm going to make, if you don't mind, I'm going to make Y max 0.2. Let's get with you guys. That's above 0.1666. Then when you hit graph, oh look at that. That's what it's supposed to look like. And if you can clean it up even more if you want to, you can dump, I think Kate, you told me this before, change your Y min to 0. Whoops. It didn't like that?
Put it in 1.
Oh hell, sorry. There we go. Thank you guys. There we go. Now the reason I set that X max to 13, the min was 2. This is actually 2 right here, which means that's 3. That point on the line is 3. So this bar represents the number of 2s. Number of 2s, number of 3s, number of 4s, 5s, 6s, 7s, highest bar. 8, 9, 10, 11, and there's your 12. So if you cut it at 12, you won't see that bar. The bar will be off the screen. Same trick we always have to do when we're making histograms in a team. I hate it. I do. Making a histogram on the TI is a total pain in the butt. So what I went ahead and did with your guys, hopefully with your guys' permission, is I set up a little experiment instead. What I'm going to do is I'm going to have Excel roll some dice for us. So right now, this is just like the one we did in class yesterday with the pie chart. Matter of fact, you'll see those pie charts down here. These pie charts represent 2 individual dice being rolled. This histogram, take a guess what it's going to show you.
Probability of the sum of it.
The probability of the sum of the pips. Yes, Megan, go ahead. I'm sorry, go ahead.
That's what I said.
Okay, excellent. So what we're going to do is, I'm going to press F9, roll some dice, roll some dice, roll some dice. So what I'm doing right here, this would be the equivalent of you guys throwing a pair of dice, looking at what you get. Looking at what you get. Now right now, you look at that, you're like, I don't see that same shape. Of course you don't. You haven't done it enough yet. Let me see if I can set this up. I did this yesterday. Stapler. There we go. Now the only problem with this, and this same thing happened yesterday, this won't update until I lift the stapler and put it back down again. So, unfortunately, for right now, just look, the trials are going up, a few hundred trials. Look at the probabilities in this column right here. Are those numbers beginning to look somewhat familiar? Somewhat familiar. What's 1/36 as a decimal? 0.0277777, which is roughly 3%. Which is also what should be down here. And you got to remember, what you're seeing, that's real quick, right? Here we go. There you go. Exactly. Not magic, what did you say that?
No, I said a bell.
Oh, a bell shape. It's actually not a bell shape, believe it or not. It's a perfect pyramid. It's straight lines. Think about why. And this is a little bit mathy, not statty. But if you think about the change in the probabilities, the slope of the change, it's constant. Every time you move over, sorry I mentioned slope in here, I apologize. But every time you go up 1 on the x, you go up 1/36. So it's up 1/36 over 1, up 1/36 over 1, up 1/36 over 1, up 1/36. And then you get to a point where it levels off and then it goes down 1/36 over 1, down 1/36. So a bell curve would actually do kind of this. The slopes would change. They'd start very narrow. Exactly. So this is a very unique distribution. If you had to use words to describe it, if you had to use words to describe this curve, what words would you use?
Triangle?
Pyramid.
Oh, good. I like that. Well, I was getting it more. No, that's perfect. That's perfect. Triangular. I was looking for more words we already use in this class. What words do we already have that describe this distribution pretty well?
Symmetrical.
Symmetric. I would definitely call it symmetric. It's pretty much the spitting image of symmetry. Yes.
Symmetric steep belt?
It's not a bell though.
It's unimodal.
It's unimodal for sure, isn't it? It's got a mode right at 7. Right at 7. And it's definitely symmetric. Yeah. So all those words work. It's bell-shaped enough. If you want to use the bell-shaped standard deviation idea, it's like bell-shaped enough to get that job done. But it's truly, and you can see we still have experimental error even after almost 1,400 trials. That's at 17% like it should be. But look at these guys. This guy got out to a running start and we haven't caught him yet. What I'm going to do is, for a little while, I'm going to let this guy run, turn the screen off, and we'll come back to him. We'll come back to him. So right now, 8's out ahead. It looks like so's 10. We'll come back to these guys. Turn this off. What I want you guys to do is give me the average and the standard deviation around the sum that we get. It's pretty obvious what the average is after what Kate and Harrison just said. But what I also want to know is what the spread is, what the standard deviation around that is. Let that guy run a little bit longer. Mute. Oh, what the hell? Let it run. Why not?
In order to
Let it
figure
run.
out like the optimal number of rolls you get, couldn't you?
Say that again.
Okay, because you're trying right now to figure out the optimal number of rolls.
Can I rephrase it, Smidge?
Yeah.
What I'm trying to do is I'm trying to force that graph to represent the perfect probabilities as close as I can. Go ahead.
So remember how in the project for Max's seeds,
Yeah.
couldn't you put like 0.99999 on the one side and then back solve using?
Yes, absolutely. Back solve for n. How many rolls? Harrison, absolutely beautiful. You can actually describe a power calculation in Math 244 by saying that. How many people do we have to go sample
In order for it to show.
in order for an effect to show? That's how you do what's called a beta or a power or a 1 minus beta power calculation in 244. Yeah, I totally could. If I don't want to be off by any more than 0.01% or 0.001% and back solve. I will never ask you to do that on an exam, just so you know. Just so you know. It's too mathy. It's too mathy to do. I mean, we've done enough math today already. That damn absolute value equation over there.
They would just looked at it.
Yeah, that's enough. It's just that. Got an average? 7. Standard deviation? Be got quiet. What's standard deviation?
2.4.
2.4? There we go, 2.4. And the reason why you can't treat this as an exact bell curve is if you tried to, you could look at it and go, okay, it's a bell curve. Looks bellish, right? Looks bellish. If it's a true bell curve, 95% of the data should be within 2 standard deviations of average. 3%, the extreme 3% is here. There's an extreme 3% out here, yeah? Which means the usual data should be essentially ish here, which is between 2 and 12. So if you will, if you were kind of finagling here a little bit, 3 is like the smallest usual value. 11 would be the biggest usual value, and you could reverse engineer the standard deviation that way. And it's pretty damn close. If you call this the normal 95%, these standard deviations around 2, not 2.4. It's a little bit less. It's 2, not 2.4. That's damn close. That's damn close. It also means that 2 is a what? And so is boxcars. Isn't that interesting? This is the, boxcars is 12, two sixes. There's clever names for all the rolls in craps, which is why craps is so appealing, right? You can crap out by rolling snake eyes in the beginning, but it's an outlier, and people have an intuitive feeling for that. When you look at craps is the most amazing, and I'm going to have you guys analyze it later in the course. It's actually got better odds on the first roll. Actually, it's got better odds in general if you do a simple bet than a roulette wheel, which probably doesn't make a whole lot of sense if you think about it. A roulette wheel seems completely even until you look at it very carefully and realize there's 2 green spaces on it. And it's almost 50-50, but craps is even more 50-50 because of the way they've set the rules up. The rules for craps, we'll analyze it later in this course. The rules for craps are fascinating. Fascinating on just a straight old line bet. And they're almost 50-50, but they're just not 50-50 enough to not make the casino money. So you'll lose your money. just slowly over time, but you'll lose it on average. And we'll get into that today too as we talk about something else. Fair enough? There we go. Still haven't caught up? Still haven't caught up yet. And unfortunately, I have to shut this thing down. Damn it. To shut it down because we have to move on to the next distribution. But doesn't matter. Harrison, we'll get there to quell your concern. Just our infinity wasn't long enough yet, basically. But I want to talk about gambling. Because I want to tie this into your car insurance payment. I do. I want to